Hello everyone, my name is Gustavo Vargas Hakim, and I'm a master's student in artificial intelligence at the University of Veracruz in Mexico. I have had the pleasure to collaborate with Dr. Galvan, and I am here to present you a brief introduction to a very interesting topic which is called evolutionary deep learning. I believe many of you have heard about deep learning and all the amazing applications we have already for many research areas, for example, computer vision in object detection, and for example, image segmentation, the synthesis of like fake data. For example, these are fake faces, but also in many other aspects of computer vision. For example, sound classification, programming languages translation, which I think is pretty cool. A real language, natural language translation, which is for example used in Google Translate, and of course beating people in their favorite board games. So there are many people that has advanced deep learning. However, these gentlemen are the three musketeers of the area because their contributions continue to be the foundations for many of the research work that has been done in recent years. But everything started with the perceptron, invented by Frank Rosenblatt. The perceptron is a very simple model of a neuron. It takes data, which can be represented, for example, by three attributes, x1, x2, and x3. This is just an example. And the perceptron computes a linear combination of these features. In this case, based on the weights W1, W2, and W3, we're going to have this equation, which is very similar to a linear regression. This allows us to generate a linear separator in data, just as in the plot in the left side. However, if we want to separate data with a more complex pattern, we would need to feed this linear combination to a nonlinear function, which is going to call activation function. And we could have, for example, the plot in the right side. We're separating data, classifying data with a more complex pattern. If we stack all these perceptrons in, for example, in this architecture, we would have what we call a neural network or a multi-layer perceptron. And what we get is more complex data separator, like in this plot. So we can think of a neural network as a function approximator that allows us to separate data in a very interesting way. Now we have lots of new types of neural networks, but one of the most important, most popular are the convolutional neural networks, which are, I think, by far the most important architecture in deep learning. They are perfect for array-like data, such as images. We know that an image is a matrix of pixels in which each pixel represents an intensity of color. So, for example, if we're working with a grayscale image, each pixel has a value of from 0 to 255 in most cases, representing a pixel in color more black or more white. The CNNs have two main operations, which are convolutions and pooling. In convolution, we have an image, for example, let's say this green square, and we have a convolutional filter, which is the yellow square. The convolutional filter has several values, which are called weights, and the filter is going to be slided to the image, and we are going to be applying an inner product between matrices. So that we have a convolved feature map, which is this pink square, which it's considered to extract certain characteristics from the image that will allow us to classify it. On the other hand, we have pooling. In this case, we have an image, for example, the blue one, and we're going to have a kernel, which is the darker blue one. And this kernel is empty. What this kernel does is just extract the largest value it can see. For example, in this case, we're sliding this kernel, and we're going to take the biggest value that the kernel is allowed to see in that position. This is called max pooling, and it's expected to undersample images. So we have a more compact representation of the features that the convolutional layer has obtained. If we stack these two operations, we're going to have a fully functional CNN. As you can see at the end, we just put a multi-layer perceptron to perform classification. For example, if we have a handwritten digit here, we would like to classify this image between 0 to 9, depending on the written element here. And this is how we construct a convolutional neural network, which is pretty simple, I think, but very powerful. However, when we're going to design these networks, we need to take into account several things. For example, how many convolutional layers we're going to have, how many pooling layers, what is going to be the size of the convolutional filters per layer, and the kernel sizes for pooling layers, how many fully connected or multi-layer perceptual layers we're going to consider, how many neurons per layer, and many more. So as you can see, this is a very complex problem to design a convolutional neural network. And of course, it can be seen as an optimization problem in which we have data, we have an architecture, and we have an error function that let us know how well the data, the CNN is performing with this data. For that, we have an overlapping of evolutionary computation and deep learning, which is called neuroevolution or evolutionary deep learning. And the ideas of these techniques is to evolve the neural networks weights or the architectures. And since 2017, it has seen very interesting success in evolution of these pretty complex CNNs. And as you remember, in evolutionary computation, we have a population of solutions. In this case, each solution is a potential CNN architecture. But for this case, we need to represent these architectures in such a way that, for example, a genetic algorithm can operate with them. So that's why we need what we call a genetic encoding. We have, in our research, we have identified at least four encoding schemes, which are the binary encoding, the grammar encoding, the block sequence encoding. Here, the word should be sequence, I'm sorry, and graph encodings. For example, binary encodings are pretty useful to represent the connectivity of the networks. If these circles are, for example, convolutional layers or pooling layers, a binary string can be used to represent the connectivity between these layers. So, for example, in this case, this binary string is used to represent a connection if it's 1 and a non-connection if it's a 0. Grammar encodings look kind of difficult at first sight because they are written in the Backus noun notation for formal grammars. In this case, for example, a convolutional layer can be seen as is a layer and can be represented by a number of filters, which is an integer value in the range from 32 to 256. It has a filter shape, which is also an integer value. It has an scribe, and it has a padding, activation, bias, and other characteristics that, as you can see, are non-terminal. So they are defined by other symbols in a complete grammar. We have the block sequence encodings, which I think is the most simple, but very powerful too. It's a linear sequence of blocks in which each block is, for example, a convolutional layer, a pooling layer, or a fully connected layer. And each block comprises several of these hyperparameters that we need to tune for each layer. For example, number of feature maps, filter sizes, activation function, etc. Graph encodings are more powerful, however, more difficult to manage, although they are very flexible, for example, in this case. And as their graph, we also consider the tree representation, which is very suitable for genetic programming, as we just saw in the last video session. And finally, there are hybrid encodings, which mix the best from both worlds, for example. They are just a mixture of two or more encoding schemes. And in this way, we can take advantage of the facilities that each encoding provides us. For example, in this case, we have a sequence of blocks, but the connectivity is represented by a binary string, which is pretty useful to separate both characteristics of the network into two different search spaces. Now, that's it for today. There are some open questions about neuroevolution for convolutional neural networks. For example, which are the best encodings for a CNN? Or neuroevolution can help us understand which kind of CNN must be used for which kind of problems? On the other hand, what are the best evolutionary algorithms to use for neuroevolution? That's a very interesting question. And finally, the question that I think is the most interesting one is, can we discover new types of neural networks with evolutionary computation? I mean, neural networks pretty different to CNNs, for example. these are just open questions, and I would be very pleased if you could eventually join us in our research about this interesting topic. I hope you have enjoyed this video session. Thank you very much, and have a nice day.